Welcome. In this session, we'll tackle an interesting and challenging problem number 630, Course Schedule 3. We'll explore how to optimize the number of courses you can take within given deadlines, diving into different approaches to solve the problem. Let's get started. In this problem, we are tasked with scheduling a set of courses to maximize the number of courses we can complete. Each course is represented by two values: its duration, which tells us how many days it takes to complete, and its last possible day for completion, which acts as a deadline. The key constraint here is that we can only take one course at a time, meaning no two courses can overlap. However, we may choose to take the courses in any order. The goal is to determine the maximum number of courses we can take while adhering to these constraints. The input consists of a list of courses, each defined by its duration and deadline, and the output is a single integer representing the maximum number of courses that can be completed within their respective deadlines. To clarify this problem further, let's consider an example. Suppose we are given 4 courses, defined as follows. The first course takes 100 days and must be completed by day 200, the second course takes 200 days and must be completed by day 1300, the third course takes 1000 days and must be completed by day 1250, and the fourth course takes 2000 days and must be completed by day 3200. In this case, the optimal strategy is to take the first course, which finishes on day 100, then the second course, which finishes on day 300, and finally the third course, which finishes on day 1300. The fourth course cannot be taken because it starts on day 1301, which is after its deadline. Therefore, the maximum number of courses that can be taken here is 3. Now, let's look at another example. Imagine we have only one course, which takes 1 day to complete and must be finished by day 2. Since the course can easily be completed within its deadline, we can take this course, and the number of courses we are able to complete in this scenario is 1. This example highlights a simple case where there's no conflict between the course duration and its deadline, making it straightforward to include the course in our schedule. In contrast, consider an example where we have 2 courses, one that takes 3 days to complete but must be finished by day 2, and another that takes 4 days to complete but must be finished by day 3. Here, neither of the courses can be taken because their durations exceed their respective deadlines. This demonstrates how tight deadlines or long course durations can make it impossible to fit certain courses into the schedule. As a result, the total number of courses that can be completed in this case is 0. The constraints for this problem ensure that the input size can go up to 10,000 courses, and both the duration and deadline for each course can be as large as 10,000. This means the solution must be efficient enough to handle large inputs while ensuring correctness. Some important edge cases to consider include courses with very tight deadlines, where durations approach or exceed deadlines, and scenarios with large numbers of overlapping deadlines that require careful prioritization. Additionally, the algorithm should handle cases with a single course or situations where all courses can be completed individually within their deadlines. By addressing these considerations, we can ensure the solution is robust and performs well under all possible scenarios. To solve the Course Schedule 3 problem, let's first consider the brute force approach using backtracking. The intuition here is straightforward. We try every possible subset of courses to determine the maximum number of courses that can be taken while satisfying the constraints. For each course, we decide whether to include it in the schedule based on the current time and the course's deadline. This is done recursively, exploring all combinations. However, the computational cost of this method is prohibitive. With an exponential time complexity of O(2 to the power of n, this approach becomes infeasible for larger inputs, especially since n can go up to 10,000. This is why we discard the brute force approach. It cannot scale to handle the problem efficiently. Instead of brute force, we consider a greedy approach that involves sorting the courses by their deadlines. The intuition behind this is to prioritize courses with earlier deadlines since they impose stricter constraints. If we encounter a situation where we cannot complete a course within its deadline, we attempt to replace a previously scheduled course that has a longer duration. To implement this, we start by sorting the courses based on their deadlines. Then, we use a max heap, or priority queue, to keep track of the durations of courses we've scheduled so far. As we traverse the sorted list of courses, we add each course to the heap if it can be completed within its deadline. If adding the course causes the total time to exceed the deadline, we remove the course with the longest duration, as it is the least efficient use of our schedule. This approach has a time complexity of O(n log n), which comes from the sorting step and the log n time required for heap operations for each course. This makes it a scalable and efficient solution for the problem. The optimized greedy solution with a max heap builds on key observations about the problem. First, by scheduling courses with earlier deadlines first, we ensure that we respect the most restrictive constraints. Second, the max heap allows us to efficiently manage the total time spent on courses, enabling us to replace longer duration courses when necessary. Specifically, whenever adding a new course causes the total time to exceed the current course's deadline, we remove the course with the longest duration from the heap. This ensures that we are maximizing the number of courses taken while adhering to deadlines. The algorithm is straightforward. We sort the courses by their deadlines, initialize a max heap to store the durations of scheduled courses, and iterate through the sorted list. Each course is added to the heap if it can be accommodated within its deadline, and the longest duration course is removed if the total time exceeds the limit. The size of the heap at the end gives us the maximum number of courses that can be taken. This approach comes with trade-offs. On the positive side, it is highly efficient, with a time complexity of O(n log n) that makes it suitable for large inputs. The greedy strategy is intuitive and ensures we maximize the number of courses taken. However, the downside is that it requires sorting and managing a heap, which adds some implementation complexity compared to simpler methods. Despite this, the greedy approach with a max heap strikes the perfect balance between efficiency and correctness. It avoids the exponential time complexity of brute force while leveraging clear insights about deadlines and durations. By combining sorting and heap operations, this solution is both scalable and optimal for the problem's constraints, making it the best choice for tackling course schedule 3. In this problem, we are tasked with determining the maximum number of courses that can be taken while respecting their respective durations and deadlines. Each course is represented as a pair, where the first value indicates how many days the course takes to complete, and the second value specifies the last day by which the course must be finished. The challenge lies in finding the optimal subset of courses that allows us to maximize the number of courses taken without violating any deadlines. To tackle this, we can begin with a brute force approach using backtracking. First, we parse the input to extract the list of courses as pairs of duration and deadline. Next, we initialize a variable, max_courses, to keep track of the maximum number of courses we can complete across all possible combinations. This sets up the foundation for our algorithm, allowing us to explore all potential subsets of courses systematically. The core of our brute force approach is a recursive backtracking function. This function, backtrack, is defined with three parameters: index, which represents the current course being considered, current time, which tracks the total time spent so far, and course count, which counts the number of courses taken in the current combination. The first step is to define a base case. If the index exceeds the total number of courses, we update the max_courses variable with the maximum value between its current value and the course count of the current combination. Once the base case is handled, we move to the recursive case. Here, for the course at the current index, we make a decision: either include the course in our schedule or skip it. To include the course, we check if adding its duration to the current time still respects the course's deadline. If it does, we make a recursive call to evaluate this branch further, increasing both the current time and course count. Alternatively, if we decide to skip the course, we make another recursive call, this time advancing the index while keeping current time and course count unchanged. This process ensures that we explore all possible combinations of courses. Once all combinations have been explored, the output of our algorithm is stored in the max_courses variable, which represents the maximum number of courses that can be taken while meeting all deadlines. However, this brute force approach comes with its challenges. The time complexity is exponential, specifically O(2 to the power of n), as we are exploring all subsets of courses. While this is computationally feasible for small input sizes, it becomes impractical as the number of courses grows. Despite its limitations, this approach provides valuable insights. For example, the constraint current time plus duration equals last day ensures that only valid schedules are considered, while the backtracking process guarantees that no possible combination is missed. Moreover, there are opportunities to optimize this approach. Sorting the courses by their deadlines can help prioritize those with tighter constraints, and techniques like memoization can reduce redundant calculations for overlapping states. These insights pave the way for more efficient algorithms. Now, let's look at the data structures involved in this approach. First, the courses are represented as an input array of pairs, where each pair contains the course's duration and deadline. Sorting this array by the deadline isn't mandatory for the brute force approach but can significantly improve efficiency in optimized solutions. Next, the recursive backtracking function inherently relies on the call stack to manage state transitions. Each state is defined by the current index, the accumulated time, and the number of courses taken. Additionally, we use a global variable, max_courses, to track the best result found across all recursive calls. This variable is updated whenever we encounter a new maximum during our exploration. Together, these data structures facilitate the systematic exploration of all possible course combinations while ensuring that our results are consistent and valid. To better understand how the algorithm works, let's walk through an example. Suppose the input courses are 3, 10, 2, 5, 1, 3. We start with the first course at index 0, with current time and course count both initialized to 0. For the course 3, 10, we consider two options, including it or skipping it. If we include it, current time becomes 3, and course count increases to 1. If we skip it, both current time and course count remain unchanged. We repeat this process for the subsequent courses 2, 5, and 1, 3, exploring all possible combinations of including or skipping each course. As we proceed, we track the maximum value of course count across all valid schedules. In this example, the optimal solution includes the courses 2, 5, and 1, 3, resulting in a maximum of 2 courses. This demonstrates how the algorithm systematically evaluates all possibilities to arrive at the best outcome. Let's break down the solution to LeetCode problem number 630, course schedule 3. First, the goal is to maximize the number of courses we can take while ensuring all deadlines are met. Each course has a duration and a last day it must be completed by. To solve this efficiently, we use a greedy algorithm combined with a max heap. Explanation of the code. 1. Sorting courses by deadlines. We start by sorting the courses based on their last day. This ensures that we consider courses in the order of their deadlines, making it easier to decide which courses can fit within their allowed time frame. 2. Using a max heap. A max heap, simulated using Python's heap with negative values, is used to keep track of the durations of the courses we have taken so far. The heap allows us to efficiently remove the longest course if needed. 3. Iterating through courses. For each course, we add its duration to the total_time, representing the cumulative time of all courses taken so far, and push its duration onto the heap. If the total_time exceeds the current course's deadline, last day, it means we cannot take all the courses we've chosen so far. Therefore, we remove the longest course, the one with the largest duration, from the heap to free up time. This is done by popping the max heap. 4. Returning the result. At the end of the iteration, the size of the heap gives us the maximum number of courses that can be taken without exceeding any deadlines. This is because the heap only contains courses that fit within their respective deadlines. Complexity analysis. Sorting the courses takes n*log n, where n is the number of courses. In the worst case, each course is pushed and popped from the heap once, resulting in a heap operation cost of n*log n. Therefore, the overall time complexity is n*log n. The space complexity is n, due to the heap. This solution is both efficient and elegant, leveraging a greedy approach and heap data structure to solve the problem optimally. Here, we start by importing the necessary libraries and defining our solution class. The main method, scheduleCourse, takes a 2D array courses as input, where each course is represented by its duration and deadline. The first step in our implementation is to sort the courses based on their deadlines. This ensures that we always consider the courses with earlier deadlines first, which allows us to make optimal decisions. We then use a max heap, implemented with a priority queue, to keep track of the durations of the courses we've selected so far. The variable total time keeps a running sum of the durations of these courses. For each course, we add its duration to total time and push this duration into the max heap. However, if adding this course causes the total time to exceed its deadline, we remove the longest course from the heap. This strategy ensures that we always prioritize shorter courses while respecting deadlines. By the end of the loop, the size of the heap represents the maximum number of courses that can be taken. Finally, the method returns the size of the max heap, which gives us the total number of courses that can be completed within their respective deadlines. This approach is efficient because we use the heap to dynamically manage the courses we've selected, ensuring that we only keep the most feasible combination. By iterating through the sorted courses and maintaining the heap, we achieve an optimal solution that balances the duration of courses with their deadlines. This completes the implementation of the solution in Java. Here, we have an example where all courses can fit within their deadlines. The input consists of 3 courses, each with a duration and a deadline. First, we sort these courses by their deadlines, resulting in an order that helps us prioritize earlier deadlines. Next, we initialize a max heap to keep track of course durations and a variable to track the total time spent taking courses. Now, we process each course one by one. For the first course, which has a duration of 100 and a deadline of 200, we add its duration to the total time, bringing it to 100. We also push the negative of the duration into the max heap. Since the total time is still within the course's deadline, there's no need to remove any course. Similarly, for the second course with a duration of 1000 and a deadline of 1250, we add its duration, update the total time to 1100, and push the negative of the duration into the heap. Again, the total time is within the deadline, so no courses are removed. Finally, for the third course, we add its duration of 200 to the total time, making it 1300, and push its negative duration into the heap. The total time still fits within the deadline, so no courses are removed. In the end, the size of our max heap, which represents the number of courses we managed to take, is 3. Therefore, the answer is 3. Now, we have a scenario where some courses need to be removed to fit within the deadlines. After sorting the courses by their deadlines, we start with an empty max heap and a total time of 0. For the first course, which has a duration of 100 and a deadline of 50, we add the duration to the total time, making it 100, and push the negative duration into the heap. However, the total time exceeds the deadline for this course. To fix this, we remove the longest duration, which is 100, from the total time, bringing it back to 0. Moving on to the second course with a duration of 50 and a deadline of 150, we add this duration, updating the total time to 50, and push its negative duration into the heap. Since the total time is within the deadline, no course is removed. For the third course, with a duration of 200 and a deadline of 200, we add its duration to the total time, making it 250, and push the negative duration into the heap. This time, the total time exceeds the deadline, so we remove the longest duration, which is 200, reducing the total time back to 50. At the end, the size of the max heap is 1, meaning we could only take one course. Hence, the answer is 1. Here, we look at a scenario where all courses exceed their deadlines, making it impossible to take any of them. After sorting the courses by their deadlines, we initialize an empty max heap and set the total time to 0. The first course has a duration of 100 and a deadline of 10. Adding the duration to the total time brings it to 100, and we push the negative duration into the heap. However, the total time exceeds the deadline, so we remove the longest course, resetting the total time to 0 and clearing the heap. For the second course, with a duration of 200 and a deadline of 20, we add its duration to the total time, making it 200, and push its negative duration into the heap. Again, the total time exceeds the deadline, so we remove the longest course, reducing the total time back to 0. Similarly, for the third course, with a duration of 300 and a deadline of 30, we add its duration, update the total time to 300, and push the negative duration into the heap. The total time once again exceeds the deadline, so we remove the longest course, resetting the total time to 0. In the end, the max heap remains empty, meaning no courses could be taken. Therefore, the answer is 0. In analyzing the time complexity of our algorithm, we start by considering the step where the courses are sorted based on their deadlines. This sorting operation has a time complexity of n*log n, where n represents the number of courses. After sorting, we iterate through all the courses, which introduces another layer of complexity. For each course, we may perform a heap operation. Specifically, when we use the heap.heap push to insert a course duration into the heap, the operation takes O log k time, where k is the current size of the heap. Since the heap size is bounded by n, this remains efficient. Additionally, if the total time exceeds the current course's deadline, we may need to pop the longest course from the heap using heap.heap pop, which also takes O log k time. These operations form the foundation of our time complexity analysis. Now, in the worst-case scenario, for every course, we perform both a heap push and potentially a heap pop. This results in O log k *2, which simplifies to O log n operations per course. Combining this with the iteration over all n courses, the total cost of this step is O n log n. When we add this to the sorting step, which is also O n log n, the overall time complexity of the algorithm becomes O n log n. Shifting focus to space complexity, the main contributor is the heap used to store the durations of the selected courses. In the worst case, all n courses could fit into the schedule, meaning the heap would contain n elements, resulting in a space complexity of O n. Additionally, since the input list of courses is sorted in place, no extra space is required beyond the input storage itself, keeping the space usage efficient. In addition to the heap and input storage, the algorithm uses a few auxiliary variables such as duration, last_day, and total_time. These variables require a constant amount of space, or O1. When we combine all these factors, the total space complexity of the algorithm is O n, dominated by the heap storage. To contrast this with a brute force approach, consider a method that generates all possible subsets of courses and checks each subset against the deadlines to determine the optimal solution. This approach would involve iterating through 2 to the power of n subsets, each requiring validation, leading to a time complexity of O2 to the power of n *n. The brute force approach also requires O n space to store temporary subsets and auxiliary variables. Clearly, the optimized solution is far more efficient in terms of both time and space. The optimized solution we've implemented utilizes a greedy strategy combined with a max heap to efficiently manage the selected courses. This allows us to reduce the time complexity to O n log n, which is a significant improvement over the brute force approach. The space complexity remains O n, comparable to the brute force solution, but without the overhead of storing all possible subsets. Now, considering the best, average, and worst-case scenarios, the time complexity remains consistent at O n log n due to the dominance of the sorting and heap operations. In the best case, all courses can be scheduled without exceeding their deadlines, resulting in minimal heap operations. In the average case, some courses are removed from the heap due to deadline constraints, leading to a balanced number of push and pop operations. In the worst case, every course exceeds its deadline, requiring both a push and a pop for each course. Despite these variations, the time complexity remains O n log n across all scenarios. Finally, let's solidify our understanding with a mathematical breakdown of the big O complexity. The sorting step requires O n log n, which dominates the algorithm. Iterating through the n courses, each involving O log n heap operations, contributes another O n log n to the total complexity. Adding these together, we arrive at a time complexity of O n log n. For space complexity, the heap is the primary contributor, requiring O n space in the worst case. This linear space usage ensures that the algorithm remains efficient and scalable. By combining these properties, the algorithm achieves optimal efficiency compared to the brute force solution. This balance of time and space complexity makes it a robust approach for solving the problem of scheduling the maximum number of courses within their deadlines. One of the most common pitfalls in solving scheduling problems is failing to account for all the constraints. For instance, a solution might overlook whether a course's deadline conflicts with another or forget about limits on the number of courses that can be taken simultaneously. Missing these constraints often results in incorrect or incomplete solutions. Another issue arises with inefficient approaches, especially for large inputs. Using brute force, such as generating all possible course combinations, can quickly become computationally infeasible as the input size grows. It's critical to identify ways to optimize your solution early on. Additionally, relying on a greedy algorithm without proving its correctness can be risky. For example, if you always pick the course with the earliest deadline, it might seem intuitive but fail when course durations vary significantly. Lastly, edge cases often trip up solutions. Scenarios like empty input, a single course, or cases where no valid schedule exists should always be tested to ensure your solution handles them gracefully. Choosing the right data structure is another area where mistakes are common. For example, using a simple list instead of a priority queue can dramatically increase runtime and scheduling problems that involve frequent updates or dynamic constraints. A priority queue or even a balance tree is often the better choice for such cases. Now, in interviews, it's also important to understand that standard problems are often modified by adding constraints like prerequisites or limits on overlap. This means you need to be adaptable and ready to tweak your approach as necessary. When explaining your solution, start with a brute force method to demonstrate your thought process, then refine it step by step. Transitioning to a greedy or dynamic programming approach can help you highlight optimizations. Additionally, always validate your solution with small test cases and edge cases to show its robustness. If you're considering multiple approaches, such as greedy versus dynamic programming, clearly explain the trade-offs in terms of time and space complexity and justify the method you ultimately select. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 630 itself is a classic case of scheduling with constraints, while LeetCode 435 focuses on non-overlapping intervals, a problem often solved with a greedy strategy. LeetCode 452 adds a unique twist with interval scheduling applied to bursting balloons, and LeetCode 1029 takes on a decision-making angle with two-city scheduling using sorting and greedy techniques. Now, when it comes to alternative approaches, dynamic programming can be particularly useful for problems with overlapping subproblems, such as maximizing the number of courses while meeting prerequisites. However, this often comes with higher space complexity. Greedy algorithms, on the other hand, are well suited to interval scheduling, where you might prioritize courses by their deadlines or end times. The trade-off here is that greedy methods may fall short for problems with intricate dependencies. For smaller inputs, backtracking can explore all possibilities, but its exponential time complexity makes it impractical for larger datasets. Finally, a priority queue or heap is highly efficient in scenarios requiring frequent dynamic updates, though it might involve a more complex implementation compared to simpler greedy methods. Great job! Today, we explored how to maximize the number of courses you can take while meeting deadlines. We discussed different strategies, from brute force to an optimized solution using priority queues. Remember, mastering these problems enhances your problem-solving skills and prepares you for real-world challenges. Thanks for watching, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!